Hello everyone, welcome back to another video in the Transformers from Scratch explanation and implementation series. In the last video, we saw about each of the components present in Transformer at the lower level, which is positional encoding, attention, and feed forward. Now we are going to move up one level and we are going to see how encoder and decoder works, and we'll also see how the transformer is trained and what happens while we do inference, because decoder is generative, so how the tokens are processed, and finally we'll also see how to visualize the attention. So guys, before moving into the video, I would like to remind you all about the announcement, and if you are a new viewer of the channel, I would recommend you all to watch this right now, because I've made a recent announcement in the community post stating that we are going to have a quiz hereafter at each month, and the winner of this quiz will have a chance to either work with me or win a 500 rupees coupon in Amazon. It's up on the winner's choice, and to know about the rules of the quiz, please stay till the end, and in the end of this video I would have said about the rules for the quiz, because the quiz will be based on this series, Transformers from Scratch explanation and implementation. So without wasting time, now let's move on to the video. Let's start with encoder. Encoder is a component which is used to understand the context of the given input so that it will provide a better representation, or it has better understanding of the text. How an encoder works. I'll have start token. Since we are doing text classification, let me consider an example like that. I am feeling good. Okay. So this is the series of tokens which will act as our input. We'll tokenize these. That will become our input. Till this, it will happen in tokenization. Now what happens is we'll compute the token embedding. By end of this video, we'll also see about tokenization. What happens in token embedding is that each word has a map to it. Let's say I will be mapped to a number named probably 0.256, something like that. It will be an array. Okay. For I, there will be a number 0, let's say it is 9, and for 9 it will have an embedding array. So to know about embedding, I have covered it detailed in the first video itself. Please check it out. Okay. So the token embedding, once it is computed, will also compute positional encoding, which tries to encode the position of the sentence, which is 0, 1, 2, 3. It will try to encode this position. Now we'll try to add both of these, and that becomes our input, which is provided to, this is where the encoder starts, wherein first we'll move on to attention, right? So what happens is this will be combined as a single entity known as input embedding, which is then copied thrice, which will become your Q, K, and then V. This is your query, key, and value. So to understand better, let me consider this as our example, where we'll have the token length to be 4 here, and we have one sequence, right? So it will be 1 cross 4, and our embedding dimension is 512. So initially our token embedding dimension will be 1 cross 4 cross 512, and our positional encoding dimension will also be the same, 1 cross 4 cross 512, and same will happen with input embedding as well. Alright, so the similar thing will happen with query key values as well. It will be 1 cross 4 cross 512 each. Okay, but all of those are until it moves on to multi-head attention. Alright, first we'll split these into heads, number of heads. So let's consider it to be 8. The dimension of query would become, or query key value, all of those would become 512 divided by 8, which would be 64. Okay, now the query would be 64, key would be 64, and value would be 64, but it will be something like this. Okay, 1 cross 4 cross 8 cross 64. Okay, so this is how the dimension would be now, and for each head we'll try to provide all of those together. Okay, Q, K, V. Alright, so this is how the input would go. And right now the dimension is 1 cross 4 cross 8 cross 64. Alright, so this is how the input is provided now. And now what happens is we'll take the query alone of each head and multiply with K transpose. Alright. So here the dimension would be something like 1 cross 4 cross 8 cross 64. But here it would become 1 cross 4 cross 64 cross 8. Alright. So that we would return with something like 1 cross 64 cross 64. Alright. 1 cross 4 cross 64 cross 64. So this is how it will happen. And this would be your query key transpose. Next, what we'll do is we'll try to do softmax of this. Before that, we'll divide this by root of dk, and dk would be your head dimension, which is 64. Okay. So whatever value is there, it will be like query key transpose by 8. Alright. So this input would now be softmaxed and would be multiplied by, actually it should be something like square here, and would be multiplied by our value, which is again 1 cross 4 cross 8 cross 64, which will again return us with the same dimension. Alright. Query key value will become 1 cross 4 cross 8 cross 64. So this is how usually in attention things will take place, and this will be your one head output, and this is concatenated. Okay, so here you will have multiple heads. It is 8 here, so all those 8 will be concatenated, and if you do that, it will become 1 cross 4 cross 512 again. Okay, it was 1 cross 4 cross 512 and it becomes 1 cross 4 cross 512 again, and here we'll add this input embedding onto this attention output. Okay, so that is our residual connection, and here what happens is we'll pass this to our feed forward, so that would be in 4 times this dimension. Okay, so here it would become 1 cross 4 cross 2048, and then again it would become 1 cross 4 cross 512. Okay, and then finally we'll have our output. This is our encoder output, and that would be copied twice as our key and value for decode. Okay, now we have a flow of how transformer work. So let me say in encoder why the representation is better. Okay, see, let's say I have an example. I am writing about attention. Okay, in encoder we'll have the visibility for all the tokens. Okay, so the mask would be 1 for all of these, and since the mask is 1 for all of these, you will have a better understanding of the context. So given a token, you will have an understanding that okay, these are all there. Okay, so that is how in encoder it works, and that is why decoder is not good for understanding the context, because you'll mask all of these tokens. Okay, don't worry about the mask, I'll explain that in decoder, but just have an understanding that why it is better to understand the context with the help of encoder rather than the decoder. Okay, it is because it has a visibility for all the tokens, and in BERT you will have bidirectional attention. Basically in encoder also it would be bidirectional. Okay, so given a token, you will have a visibility for the tokens coming before it and after it, so that it has a better idea of what it is speaking about. Okay, here for writing only there can be some options like speaking or talking, something like that. I am playing about attention doesn't make any sense, right? But if I had generated it as I am, playing would have been more sense than writing, and since we are saying about attention, it makes more sense to have these two tokens. Okay, so that is why contextual capture or contextual understanding is better with encoder. Okay, so given a token, finally you'll have an output which is of the same dimension as input. So that is how an encoder works, right? So to have an understanding about each of those components which I spoke about, which is multi-head attention, the positional encoding, and residual connection here, please check the last video, because in that I would have explained in deep about the math in each of the components. Alright, and if you want the link is in the description, as well as I've pinned it in the I button, so you can check it out from there also. Now we'll see about decoder, and decoder is more interesting because it learns by a method known as teacher forcing. Okay, So what happens is, now I'm not gonna dive deep into the shapes and all, because now you would have an understanding about the shapes with this encoder itself. So now I'll say how the tokens will be processed, because in encoder it will be very normal, but in decoder, since we are generating it with the mask, look ahead mask, it will be slightly different while it is being trained. All right. So in decoder, what happens is, I'll write it as a simple one. We have embeddings, which is passed into masked multi-head attention. I'll write it as masked MHA, which is then passed on to multi-head attention, which is then to feed forward, and finally a projection layer and output. Okay, so this is the flow basically. And the thing which is going to differ is here the masked multi-head attention and multi-head attention. Since multi-head attention is a cross attention, okay, it's not self attention, it becomes cross attention, and masked multi-head attention uses something called look ahead mask. Okay, unlike the normal multi-head attention will have a mask only for pad tokens as 0 and normal tokens as 1. This masked multi-head attention makes sure that at any given token, only the previous token is being visible. Okay, so let me say about the mask first, which is look ahead. So given an input stating I am writing now, what I would do is I'll provide an array of input. Okay, it will be 1 0 0. Let me consider I'm writing. Okay, so that it will be faster. 1 1 0 and 1 1 1. Now this mask would become our input mask. Okay, usually we'll only provide this 1 1 1 as our input mask, but here we'll try to provide this as our input mask. Okay, now you might wonder, Vasant, now I'm saying I want to generate the next token, so how it happens? Okay, so that is where teacher forcing comes into picture. The first token would be start token. I'm not considering here. Let's say it is start token already there. So what happens is it will try to force based on this ground truth we have provided as labels. The loss function will take care of itself, and it will try to say, like, it could have been like something like he. Okay, it will try to force it towards I, and then it would become something like he is. Now since it is I, it will become I is, and then now is not possible. The loss will again try to force it as I am or I was. Okay, and then again the loss would see like, okay, the loss for I was is higher, and for loss of am it is lower, so I'm going for am. Okay, now the tokens I and I am are generated. Now you have the input being like this: I is there, I am is there. Now for I am, you have lot of possibilities. You have playing, writing, speaking, or sleeping. Okay, there are a lot of options there. Now the teacher here means our ground truth. The ground truth drives the generation. Okay, while training, the ground truth drives the generation, where it will say like, okay, you ought to generate I can't accept any of the other tokens you will generate at that point. If you are going to generate any other token other than I'm going to reduce your marks by providing higher loss. Okay, so similarly, since there are a lot of possibilities here, the model will try at the first epoch probably as play, and then in the second epoch it will try it as sleep, and the score would have been like probably lower, very very lower, and then it will see like, okay, I have another option, right? Let me see here. Okay, it's higher. Okay, I found the token, so it is I'm writing. Okay, if it is full stop, again for full stop a token should be generated. All right, it will see like, okay, I'm writing. There is another possibility. Let me see. There is about, on, and then full stop. Okay, about, though it makes sense for me, the ground truth or the teacher is saying, okay, I don't want you to continue. Okay, I have higher loss here. My performance has gone down. So similarly, it has happened with on as well. But when I generated full stop, the teacher is providing me good marks, reducing my loss. So which means dot is my next token. So this is how teacher forcing happens. Teacher forcing happens at each token. Okay, while you generate each token, the teacher will force you to generate the correct token, but this will happen only while training. Okay, so that is how the token would work while using decoder. but that is only during masked multi-head attention. Okay, in masked multi-head attention, that is what is making this obviously auto-regressive in nature, and that is where you need teacher forcing. Okay, but like I said, decoder is not very good with context understanding. Like I said, see, I am writing about attention, right? If I consider this writing depends on these two tokens. Okay, so it needs to have an understanding of both. Let's say I'm asking what I'm writing about. Okay, so to complete this, I am writing about attention, it needs to have an understanding of both, right? So what happens is the encoder would have seen this input. Okay, the encoder would have seen this input, and that will provide the context for answering this question. Okay, it will become our key and value. I told you, right? While in encoder, that will have two copies of the output. Okay, where is it? Yeah, here you can see, right? These two would become our input for cross attention in decoder. Okay, I've covered cross attention in detail, but I'm covering a gist about cross attention now. So what happens is, usually when you're going with the attention, right, you would need inputs like query, key, value, and mask. Okay, for self attention, given an input x, okay, it would become something like x mask. Okay, but in cross attention, to show, okay, this is where your context is. And guys, query key value is very important, and if you haven't watched it, please, before continuing this video, please watch the previous video, because query key value serves the core purpose of transformers architecture. Okay, so it would become something like x, because what I need is the query, and where do I have the key, and what is the answer I need is the value. So what answer I'm expecting, that is our query, right? So it would be from the decoder itself, query. But my answer, I know it is going to be in encoder, but I don't know where. It is the model's purpose to understand it. So let me give my encoder output here. Encoder output logic should be provided here, and the value is also there only, right? So the both key and value would be from the encoder output, and also you need to see the whole context, right? At that time, you are not seeing your answer. You are seeing, okay, this is where the context is, and I am trying to find the answer. And that time you should not restrict the model to some specific token. So we'll provide the source mask, or let's say it is an encoder mask, encoder attention. Okay, so this is the logic in which decoder as well works. Okay, so given an input, you'll try to compute the embeddings, you'll compute a look ahead mask to compute masked multi-head attention, making the decoder auto-regressive, and then you will also provide this input along with the encoder output to the cross attention. Sorry, I missed a feed forward here. After that, it will go to multi-head attention, which is the cross attention, and then finally you will also have your feed forward, and then finally your output is generated. Now we are gonna see about the code to build the transformer. In the previous video, we saw about our feed forward, attention, and then we also saw about embeddings, right? Now we'll cover the rest. We'll cover with encoder, decoder, the training code, inference code, and we'll also see about the tokenizers, how to train a tokenizer, and also we'll complete finally with the attention visualization. So let's start with encoder, and for encoder we are importing multi-head attention class from attention.py, feed forward class from feed forward network, residual connection and layer norm from layer norm, because these are going to be our building blocks for the encoder and decoder as well, which we know from the previous videos. Alright, so here we are first initializing the classes which will become our layers. So here you can see we have our D model, which is our embedding dimension being 512, the number of heads being 8, attention dropout we have provided as 0.2, feed forward, residual dropout, everything is 0.2. okay, and all are provided to self attention and feed forward. Okay, so let me fire up the paper. Now it will be easy for you to compare and understand how we should build a model based on the paper. Alright, now we have our encoder code and the architecture side by side. So let's compare and see. Right, now we have a multi-head attention which is initialized with the embedding dimension the number of hits and attention dropout. Okay, and then we have initialized our feed forward as well, along with 2 residual connection. As you can see here, we have 1 and 2 residual connection. For that, we have provided 2 residual connection in here. Alright, and then we also have embeddings here, which is out of the encoder. Alright, the encoder is in here, but the embeddings are out of the encoder, so that wouldn't be a part of the encoder block. Why it is encoder block? Because this is just one block and we are going to keep n blocks which will be stacked together to form the encoder. Alright, now we have our forward, in which what we should pass is, so let me open the residual connection 1 as well. Okay, residual connection is there, which will take a sub layer and then which will also take a input. Okay, you'll have your sub layer and input, where to the sub layer, which is multi-head attention here, you'll pass the input and that output would be added with this one, the original one. Okay, so that is how residual connection or add-on layer norm takes place. So to that we are providing our input, which is X, and for self attention, like I said before, we'll have query key values all with the same input, so we'll paste it thrice. Okay, query key value and attention mask. So now we are completed with attention, and then what we should do next is we should pass it to feed forward. Okay, so we are putting another residual connection in here, which will take the attention output and then it will run it on feed forward block. So that will become our encoder output. Okay, so this is how you need to construct a model from the paper. So what we did, first we created the core blocks, which is multi-head attention, residual connection, feed forward and all, which is the core block in here, and then we moved it up the level from 0 to 1 probably, and then now we have the encoder block. Okay, so now next one, we have our encoder block. Now we need to stack it. Okay, we need to have n layers. All right, so we'll take that num layers as input along with the embedding dimension in this encoder class, and there is this class called module list, which will comprise number of modules together, wherein here our module is encoder block. Okay, so we'll stack the encoder blocks together, and finally we'll also add a layer normalization. Okay, so what happens is, to each layer we'll pass this input and then finally the output would be normalized. Okay, so that is how encoder works. All right, easy implementation. Okay, now let's see about decoder. For decoder, it's going to be slightly complicated, not as complicated because we have our theory ready, but practically it is going to be slightly different than how it was with encoder. All right, so similar inputs, we have our embedding dimension, number of hits, attention dropout, residual dropout, feed forward dropout, and all being initialized. But you should note here we have 2 attention, which is self and cross. Okay, and then we have our residual connections as well. Guys, please listen this carefully, what I have taught till now and whatever I'm going to say before, because based on these, like I said, we have a quiz and the winner will have a chance either to do a LLM project with me, or you can win 500. It's upon your choice. Okay, or if you think, man, I'm not interested in quiz, that is also fair. You can like stay out of it and just check that if you are right. Okay, because I'll also provide the answer. Now coming on to the forward, which will take 4 inputs, which is X, encoder output, source attention mask, and target attention mask. If you see in encoder, we won't take that much. Okay, it is in X, which is that input token, and then we'll have our source attention mask. But here for cross attention, we need encoder output and source attention mask, and for masked multi-head self attention, we need a target attention mask, which would be a look ahead mask. Okay, source attention mask will be like a padding mask, and target attention mask will be like a look ahead mask plus padding mask. Okay, because padding tokens will also be 0 and the next tokens will also be 0. So here we are first computing this, which is residual connection 1, and we are calling the self attention, because here you can see, right, it is self attention. There is no inputs from encoder being passed, so we can just not worry about okay what is going to happen, and then we can just provide xxx target attention mask. But in cross attention out it is going to be different. We are going to call the residual connection 2 because we need instances of residual connection. We have made it as 1 2 3, but you can also do it as module list and call it as off 0, off 1 and off 2. That is also fine. Okay, in residual connection 2 we are passing the self attention output. Here we need to add, right? So for that we have our self attention output, which is x plus sublayer of x, right? So for x we have our self attention output, and for sublayer of x we are applying the lambda function to the cross attention, where what it will take is, it will take the self attention output, along with that it will also take the encoder output. Okay, the query is our self attention output and key and values are from encoder. Okay, and then we have our source attention mask and not target attention mask, and we know the reason for it now, right? Now this is our output of attention, which is passed into feed forward. Finally we'll get the output. Okay, so that is the decoder block, and again you need to stack it for n layers, and that will become your decoder. Okay, so that is about encoder and decoder. Now there is a difference. Okay, here you can see there is something called linear. Okay, so what we are going to do is we are going to have a file known as transformer. Okay, I'm just seeing it. Yeah, here it is. In transformer we'll combine all of these, and finally we'll have a transformer architecture ready. So for that, what all we need our embeddings, because we have it as our separate class. We need our embeddings. Input embeddings are there. We have encoder, decoder, and that's all. We have torch neural network as well, because projection layer is not done yet. This is our projection layer. The linear layer is our projection layer, and that is not done yet. All right, so here it will take demodel number of layers and vocab size, because the projection layer's job is to map the embeddings to the vocab size. Okay, so here you might work with 512, but those should be mapped to 30,522 or 50,000 in our case, because I have set a huge vocab size. So 50,000 to that it should map, and here we are doing that. Okay, so first we are creating an instance of input embeddings, which will do this computation of token embedding, which is input embedding specified here, and then it will also compute position line encoding and add it. Okay, for position line encoding we have used sinusoidal position encoding, and now we are also making an instance of encoder, which will take demodel and num layers. The number of layers we are considering it to be 2, but you can also consider it to be 6, 8 or 10, how much ever you want you can do it. Okay, so decoder also is similar, but make sure that the number of layers are same. Okay, and then finally, like I said, we are going to map, right? It is going to be 512 mapped to 50,000, right? So that is the job of projection. In one forward, what happens? First we'll compute the input embeddings. We can also simultaneously compute for target as well. We are computing for source and target. We are passing through the encoder, and encoder output is got here. So once you get the encoder output, the job is to compute for decoder, and the decoder output is computed, and finally you are doing a projection. Okay, so this is how a transformer is built. And guys, we are 50% or 60% done, because we just have the architecture. Okay, we don't have a working model or something like that, because we need to train it, right? That is what we are going to do next. But before going on to that, still, like I said, the architecture is not completed. You need to initialize the weights. Okay, now randomly it would become very random. The weights would be like 1.8, 5.6. There wouldn't be any pattern for it to start with. Okay, to start the training, we'll be initializing the weight with Xavier uniform. Okay, there is a paper which was released from Xavier Glorat. Under his name, there is a weight initialization method which is known as Xavier uniform. Okay, and we are gonna do that wherever there is a dimension which is greater than 1. Like even if there is a weight which will have more than 1 neuron, we'll just initialize a Xavier uniform weight. Okay, so that will provide our model. Now we'll move on to the next section, which is to build the dataset. Let me zoom in. For training the model, we need dataset, we need tokenizer, and then we need our training loop, right? that we are going to see next. For dataset, we have used a dataset class, wherein for dataset we are considering diarrhea emotion, and here there are 6 classes of emotion, and I'm just going to focus mainly on these two, sadness and joy, because these itself cover around 70%, and the model surely is gonna fail in these love and surprise classes because it is very less. Okay, but we'll focus on these two. And here you can see I didn't feel humiliated, and it is sadness. I don't know why it is like under sadness I can go from feeling so hopeless to damned hopeful from just being around someone who cares and is awake. Yeah, it is so hard, right? Like we would even be confused if it is sad or like some kind of expectation or something like that. And here you can see I am feeling grouchy. That is anger for sure. I am ever feeling nostalgic about the fireplace. I will know that it is still in the property. We can also say it as love. That is true. So that is about a walkthrough to the dataset. As you can see, it is a English Twitter message dataset which would be classified under 6 basic emotion, which is anger, fear, joy, love, sadness, and surprise. All right, we are considering this dataset, and for this dataset, first what you need to do is we need to create the tokenizer. Now we are gonna see about tokenizer. All right, let me take the notepad itself for me to write. We have a tokenizer section now. So what is a tokenizer? A tokenizer is a component which will do a process known as tokenization, which is a process of splitting the sentence or a sequence of words into a smaller entity known as tokens. Why I am saying smaller entity rather than words itself, you will understand that. Okay, because why we are doing tokenization is because the model needs just a sequence of tokens. Okay, this is how it needs the input. It's not like it doesn't accept this kind of format, it needs this kind of format, a list of tokens. Okay, now I'll say why we are calling it as tokens, not words. There are 3 types of tokenization. Okay, 3 types of tokenization, wherein the first type is character level, next is word level, and then the next is subword level, which is the most powerful one. Okay, well, I'll say it is the most powerful one. Don't worry. In character level, what happens is, given an input like I am writing, the tokenization will happen something like I space A M space WRITING. So here the problem is that you find it hard to understand the context. Okay, when it is token level, right, it is very hard. You have the space as a separate token. Let's say it is ink. This should be a single token, not INC. What is the difference between this full stop and a final full stop? Okay, what is the difference? No, nothing, right? Like if you put it as token, both are same. It is very hard to understand the context, and that is why this is the least preferred method. This is the least preferred method. Okay, next we have word level, which usually happens with some delimiter, which is usually white space. Okay, so now what happens is it will be like I am writing, only 3 tokens. Okay, here we have better contextual understanding, that's for sure, but the problem is vocab size will be very huge. Why? You see, there is a process in NLP known as stemming. Okay, the process involves cutting down the words to its root word. For example, if it is writing, we'll cut it down to write. If it is playing, we'll cut it down to play. Okay, so similarly a process will happen in this tokenization as well while we are using subword. Okay, so if it is I am writing, or probably better I'm playing football. Okay, let's consider this to be our total vocabulary. Usually it would be I am playing in word. Okay, I am playing football with my foot. Sorry for changing the example, because you'll understand why we need subword. Okay, with my foot, okay, here if you consider the vocab size, right, in word level it will be 1 2 3 4 5 6 7. Here, okay, it will become 1 for I, 2 for am, 3 for play, 4 for //ing, 5 for foot, 6 for ball, 7 for with, 8 for my, 9 for foot. But the unique token will be 6. That is the important thing. Okay, the number of tokens will be increased, that's for sure, but the vocabulary size for foot and football, here what it will do is it will try to do something like foot / ball. Okay, it will try to combine this foot into football. If it is like football, footballing. Okay, if there is a single token like this, what it will try to do is it will try to make it as 1, 2, 3, and the token will look like foot / ball / or # ing. Okay, so what is this hashing indicating? It is stating that there is something before this to be added. Okay, so it is saying like, okay, ing should be added to ball, so it will become foot # balling, and it is saying like, okay, still hash is there, I'll go another level, it will become footballing. Okay, I'm playing football with my foot. In this you'll have lot of tokens, but with footballing you have 3 tokens which is combined in different ways. The number of tokens increase, but the vocab size retains the same, but the context also retains. So always the best method is to use subword, but we are not going to do subword level and all, because subword level tokenizer is quite hard to create. So we'll work with word level itself, because we are doing some simple transformer task, right? We'll do for word level. So in word level, what happens? If I'm saying I am writing, it will become I am writing. Okay, so this is the tokenizer which we are training right now, and for that the code goes as follows. First, what we need to do is we need these following imports. We need load dataset, we need tokenizer. This tokenizer class is the one which will create your tokenizer, and this is from tokenizer's library, which is of Hugging Face. Okay, and then we are calling the word level model, but like I said, there is a lot of other types of tokenizer as well. And for the word level, we have word level trainer, and for pre-tokenizer, like I said, you need some delimiter to split, right? For that we are considering white space. Okay, so to initialize this tokenizer training, what we'll do is we'll initialize it with the dataset ID along with the tokenizer path where you want to save. Okay, and then we'll also provide the vocab size, which is 50,000, which is from the config. Okay, we are calling the load dataset function to load the dataset, which is dar AI emotions, and we are creating a dataset iterator because we need to train, right? So for that we are creating a dataset iterator which will provide one after another. Okay, each input will be provided, so you can ensure that okay, there is nothing called UNK token for me. Okay, that will be there. Okay, because what is UNK token is that, let's say your library looks something like I am writing. If there is a word coming like I was writing, okay, in its tokenizer library, in its tokenizer config or its vocabulary, it wouldn't have seen this was, so it will do something like UNK, which states that okay, I don't know what word was there. Okay, that, to be honest, I don't know. That is what UNK token means. Okay, unknown token. But our case, we won't face UNK tokens because the dataset in which the tokenizer is built and the dataset in which we are training both are same. Okay, since both are same, we won't face that error. But when you are using a public model, like a foundation model that is on a new dataset, probably let's say you are creating a tokenizer for English and you are expecting the model to do work with some other languages, it is going to give UNK. Okay, so that is what UNK token means. And here we are creating the pre-tokenizer, and for word level trainer there is a requirement of vocab size because it needs to know how much vocabulary I need to build, which we have given as 50,000. We are saying that special tokens are pad token, which is to pad. I hope you all know padding by right now. We have talked about it a lot. We have start of sequence token, end of sequence token, and unknown token. And we are providing a parameter known as minimum frequency to be 2. What happens is, if there is a pair, okay, like next we have the tokenizer. Since the tokenizer is ready, the tokenizer class which is being instantiated, we are training with this trainer which we created. Okay, here you can see the tokenizer has a function known as train from iterator, which we need to provide. Iterator is to be provided along with the trainer. The trainer is here. Okay, iterator is from this dataset iterator, and then we have our trainer from this word level trainer. Once you provide both, the tokenizer will be created and it will be saved in the path provided. For this, obviously I have used a dataset and that is trained. Okay, so that is about tokenization. Once your tokenizer is completed, you can move on to the next step, which is to build the dataset. So before going on to that, let me say what are the requirements for a transformer training. Requirements for training. This will be like something like our checklist. Okay, first we need model, tick, that is done. We need tokenizer, that is done. We need dataset, which we need to do. Then we need our training loop. So post training, we'll need something like an inference code. These are to be done, which we are gonna see now. Okay, so for dataset, we are initializing with the dataset ID, tokenizer, because we need to tokenize, right? And then we have our max sequence length, how many tokens we are gonna allow. Okay, and then we have our source column name, target column name. Here we are instantiating all of those, and we are calling the dataset class as HF dataset because this dataset represent PyTorch dataset. Okay, so in that we are calling the from pandas function, in which we are creating the dataset and we are sampling it. Okay, why we are sampling it? We are actually not sampling it, we are shuffling it. When you provide frac is equal to 1, it will try to shuffle the dataset. Okay, if there is in some order in the dataset, it will try to shuffle it. And we are also providing the torch tensors for SOS, EOS and pad tokens. Okay, now we need underscore len, dunderlen rather, which is length of dataset. Okay, that is required because it needs to know how much data points are there in the dataset. Next, we are having the getItem function, which is nothing but the function which will provide the data. Okay, as the name suggests. In this, it takes a parameter index of, let's say, like you have a data frame and I want this index. That happens with this getItem function. Okay, so we are calling that specific row, and then in that we are saying like, okay, source data is this and column data is this, with the help of source column name and target column name. Okay, which all are instantiated while init function itself. The encoder input tokens, what are those? Okay, first we need to encode the source data, and then we are maintaining a common data type, which is int64. Okay, so similarly we are doing it for decoder input tokens as well. And there will be scenarios where you might have tokens more than your max length. Okay, that is where you do a process known as truncation, and that is what we are doing here. Okay, why I'm considering -2, I'll say that, but right now just follow me. Okay, we are checking the size of 0. Okay, which will show the number of tokens in the input. So if it is more than 126, because our max length is 128, if it is greater than 126, we'll truncate till 126 from starting till 126. But there might be scenarios where you will have 80 tokens, 5 token, something like that. Okay, so in that time again it won't work, because in a batch everything needs to be of the same dimension, and that happens with this padding. Okay, so first we are calculating the number of padding tokens, where we are subtracting 128 minus the number of tokens -2. Why always this -2? See, in encoder input tokens, we'll pass the start of sequence token along with the encoder input token, then EOS token. Let's say your encoder input tokens is 126, then you have your start token 127 and EOS token to be 128. So here your padding token would become 0. And that is why we are subtracting it with 2. And then the same logic applies with decoder as well, because in decoder we won't use padding token. Sorry for the wrong word being used. We won't use EOS token. Okay, in decoder input we won't use end of sequence token, but in label we'll use it. Label is your ground truth. Okay, so in label pad tokens, label pad, decoder input pad, encoder input pad, it does nothing. Okay, it will try to multiply, and let's say like if it is 5 token, it will try to create 5 pad tokens. Okay, as a single array, obviously. And that is what happens. You are calculating the number of padding tokens here, and that array is created here, and you are concatenating all of those, which will give you your encoder input token, decoder input token, and your labels. Okay, next it's time for us to create the attention mask. For encoder, we know it is just padding token mask, right? So we are saying like, okay, whatever token is not padding token, I'll have it as true, otherwise it will be false. Okay, and since you are putting the torch to be in 64, what it will do is, wherever it is true, it will become 1 and the others will be 0. If it has been bool, it would have been true, false, but since it is torch in 64, it will become 1 and 0. Okay, in auto-regressive mask, we are going to build the triangle. Okay, that auto-regressive mask, it will be always square. Okay, let's say if it is 3, the sequence length is 3. So what happens is 1, 3, 3. That is what we require as ones. So what happens is it will be 1, 0, 0, 1, 1, 0 and 1, 1, 1. That is what happens with torch.try_u, and the diagonal is set to be 1. Okay, that is what is required here. And then what we are doing is we are computing the padding mask. Along with that, we are also multiplying the autoregressive mask. Okay, because like I said, it is both padding mask and autoregressive mask, which is nothing but a look ahead mask. Okay, so yeah, that will give you your decoder attention mask. So now let's see, we have our encoder input IDs, we have our decoder input ID or input tokens, and then we have our encoder decoder attention masks, we have our labels. Okay, which means we are ready for training. Okay, so let's create a dictionary which will be having the following values: encoder input IDs, decoder input IDs, attention masks, labels, source and target if you need. Okay, all of these will form our data set. Now we have completed our data set. We have created our model. So next step is to create the training loop. Okay, for training loop, what we are going to do is we are going to have a class known as trainer utils, which I'll say once we move on. Okay, in trainer utils, we have the following. Like, you can say this is the crux of the training. Okay, training file, we have kept it as simple as possible, but this one will be like having all of those function which is required for training. Okay, as you can see, it is a long file. Obviously I have made some documentation as well, that makes it very long, because at every time you can't be watching this video and all, right? So you can just go through the doc string and you will be able to understand. As the name suggests, this utils class is to hold all the utilities required for model training and inference as well. And in this, we are providing our dataset ID, we are providing our tokenizer path, which is tokenizer.json, and then we have our max sequence length, source column name, target column name, logging directory where you want to store your logs. We have our batch size and then our vocabulary size as well. Okay, and here you can see I tried a lot of attempts, so it will be clustered. In the tokenizer, first we are calling the tokenizer, which has a function known as from file. What it will do is it will take the tokenizer.json file and it will try to create an instance of the tokenizer based on that. Okay, now we are creating our model. Next, our dataset as well. So we have a tokenizer, model and dataset. So what all are needed in the training? In training, we need optimizer, we need loss function, we need the model, dataset, data loader, and the tokenizer. These are the things which is required. And if you are going to log something, we need our logger. So we are done with the tokenizer, model and dataset. So it is time for us to call the logger, which is TensorBoard logger here. Summary writer is from TensorBoard. Okay, so it will try to log things which we say we want to log. We'll log the training loss. Okay, and then we are calling the optimizer, which is Atom optimizer, the most famous optimizer, with the learning rate of 1e minus 4. Okay, the learning rate would be in config file. Okay, all the configurations are updated in this file. It is a good method because you don't want to go inside the files for you to change the configuration while training. You can just change the config file and it will have its impact. Okay, and here we are saying we need to ignore the padding token while we are calling the cross entropy loss. Cross entropy loss is a loss which will try to match the tokens. Okay, if it is 1 1 1 and 1 0 0, it will be something like 0.33, something like that. The loss has its own calculation. If you want a separate video on cross entropy loss, how it works, let me know. I'll make a short video on that as well. But here we are saying we need to ignore the pad token, because let's say you have a sequence of 10 tokens and rest 100 is like probably pad tokens. If your model generates 105 pad tokens, still your losses will be very less because pad tokens are same from the input and labels. So that is why we are doing ignore index. We won't consider our padding token for our loss function, because when we are not giving any attention to it, why should we calculate the loss for that? Next, like I said, dataset is not enough. We need data loader. So for that, we are calling the data loader, torch utils data loader, which requires a batch size, which we consider to be 10. We are shuffling the dataset as well while training. And then we are also providing the dataset class, because it takes a torch dataset class as its parameter. And for say like safety purposes, I have had it as train data loader. If you want, like, you can do a test data loader, write a validation loop, and probably you can do val loss as well, which I didn't do. Okay, to compute loss, we have this function which will compute the cross entropy loss, which will take two parameters, which is model output, which is logits, and then labels. Okay, both are needed. And here what we need to do is we need to call label dot view of -1 and logits dot view of -1 comma self dot vocab size, so that both are in the same shape for us to calculate the loss function. We'll not see the generate function right now because that is about the inference, which we'll see later. Okay, now coming on to this function in train. This is where we went inside, right? Trainer utils, which will provide all the utils you need for training. Okay, we have our data loaders, we have our writer, which is our logger, we have our model, we have our optimizer, all are provided. Okay, next we are making the model to be in CUDA so that we can use the GPUs. I have GPU, so if you don't have GPU, make it as CPUs. Okay, and we are initializing the epoch number to be 0 and step numbers to be 0 as well. Okay, the number of epochs you want to train, you can provide it from the config. Like I said, we are considering it to be 5 here, and then we have our model save path, which is transformer classifier. Okay, and then now we have our train function, which is what is called here, and here we are saying for epoch in range of num of epoch for data in TQDM. Okay, why I need TQDM? So that I can see what is going on, how many steps is completed. This will give a progress bar. Okay, so this will take the data loader because we need to traverse through the data, and we are just printing like, okay, I'm training the epoch number 1, 2, 3. For that we are using this. Okay, now we are calling another function from the trainer's util itself, which is train one step. Okay, for one step of training, this function will be called. So how many ever steps we train, that much time this function will be called. Okay, so what this function does is it will do one forward and one back propagation, and then finally it will do the optimization part as well. Okay, it will step the optimizer and it will go to zero gradient. All will be done in one step. So whatever you want to do usually in a PyTorch training at one step, all will be done in this function. So here we are calling the encoder input IDs, we are calling the encoder attention mask, decoder input IDs, decoder attention mask labels, all from the data, and we are making it to be in CUDA. So we are passing through the model. Okay, the model forward happens, we have our model output. The model output is passed to the loss function, compute loss, which we saw right now, and there what happens, we'll try to compute the loss. Okay, so once your loss is computed, you will do back propagation based on that with the help of optimizer. Once you call the optimizer that step function, your back propagation happens where you do this optimization. Like you'll update the parameters, right? Weight new is equal to weight old minus learning rate into dual by duo. It is a back propagation calculation. That optimization will happen when you call this optimizer.step, and then you have a optimizer.zeroGrad, which will empty the gradient once the step is done, and will return the model, optimizer, and loss at each steps. Okay, so it will go on. Okay, we are incrementing the number of steps as well, and it will go on till the one epoch is completed. And once one epoch is completed, as you can see here, it will try to call the save checkpoint function. Okay, the save checkpoint function, which will first call the ensure save folder. What it will do is like it will see if the folder you want to save exists. If it exists, it will not consider anything. If it doesn't exist, it will make that folder. Okay, so in that we are storing the model, optimizer, static, both we are saving, and we are also saving the number, the epoch number at which epoch I'm saving, and the loss as well. If you call that, you can understand what all have happened. But if you want, you can also compute the validation loss, the step number, all can be saved as well. We are printing that. Okay, so to train it, you can just call python train.py. You can just go into the source, but make sure you have first call the tokenizer. Okay, first do python tokenizer.py, then do python train.py. Okay, it will work. No issues, it will work. Okay, let me do a time lapse here till the training starts. Okay, here if you see the training has started and it will go for 5 epochs. Okay, so that is how you need to do training. Let me show an inference now, for which we also see about a concept known as greedy decoding. Okay, for decoding strategies, I'll make a separate video because it is a pretty huge concept by itself. But if you want that to be our next video, let me know. I'll make it as the next video. Okay. So this is the inference.py file where it requires the trainer utils as well. Okay. This train utils is required for us to use the generate function. Like I said, generate function is there. So here it was for translation before. We'll make it as classify. So here we have the classify function which starts here. Okay. You want to call it. I'm saying I'm delighted. Okay. So we are making sure that the inference happens in CPU, where first we need to tokenize, right? So first we are creating the tokenizer, we are creating the model, we are loading the state dict. Okay, the best checkpoint for me came at 3rd epoch, so I'm just loading the state dict. And since we saved with the key model, we are loading it. Okay, and we are setting it to be in eval mode so that it doesn't consume any GPU. And we are calling the no-grad function to avoid the gradient calculations. Okay. First, what we need to do, we need to tokenize. So we are tokenizing the input, and along with that, obviously we need to do that padding at the start of sequence, end of sequence token and all, which is done here. Okay. I'll also compute the source attention mask, which is done here. So once this is done, you have your input IDs, which is padded and is ready. And then you have your input mask. Okay. For output, you shouldn't do anything. That is the thing. Like I said, in training time and in, inference time, decoder works different, and let me show that how. Okay, in generate function, first we are creating the SOS index and EOS index. All right, and we are creating an empty placeholder for the decoder input. It will start with the start of sequence. Okay, SOS is called here. So what we're doing is, I'll first do the theory in here, and simultaneously I'll show you the practical things. Okay. So while inferencing, what you will do is, you will start with one token. Let's say if it is SOS, this will be passed into decoder along with obviously encoder input and all. Okay. Along with the encoder input, he will provide that. And in decoder, what you will do, you will generate a token. Okay. Only one token will be generated, not the sequence. In training, you will provide the whole mask. Okay. It will be an array, but at inference time, you will provide only one token. And then if there is another token, you will try to add this. Okay. There is nothing like this kind of a mask. Okay. Which will be complete. Like, usually in training, what you will do is, if it will be 1 0 0 1 1 0 0, something like that. But in training, what you will do is, first you will pass this one token, then you will do this 1 1 0 0 1 0 0 0. Okay. It will be 1 0 0 0. Like this. Okay, but here it would have been complete. It will be a single array, but here it will be looped. Okay, that's why we are using this while loop. So what we are doing, first we are creating it for the first token. Okay, and then the decoder input, which is obviously here only one token. So you will pass this one token in there. Okay, usually mask is not required for decoder. Let me clear this. I'll put it again. While training, you will provide it as this 1 1 0 0, like probably 1 0 0 0 1 1 0 0 1 1 1 0 and all 1. Okay, this is how the input will be like. But in inference, you will only provide this 1. In the next step, it will become 1 1. The next step, it will become 1 1 1. So necessarily, actually, the mask doesn't make any difference, but the model has its parameter as mask. So here we are just computing the mask. Okay, and you are computing the model output, which will give you the model logits. So you have your input ready in decoder. Encoder is already done. This is provided to softmax function to make sure that out of, let's say if it is one token, it will be 1, 50,000. Okay, in 50,000, which is the most one, all should be mapped to 0 to 1 probability, because this is all about probabilities, logits, and we are making sure that that specific token, which is our expected token, is having the maximum probability, which is done with softmax. Okay, softmax is nothing but an activation function which will try to have all the given input into a single probability, which is to 0 to 1. Okay, next we will call the argmax function. It will try to have or try to get the token with maximum value or maximum probability after softmax. So basically, this is what is your token. Next token. Let's say I'm saying like I am feeling. Okay, to say the next token is good / bad. This is the process. Okay, and now you'll have, let's say it is I am feeling good. Okay, till that it is done. I said like I said, until full stop the generation doesn't need. Okay, but it is not just full stop, it is end of sequence token. So we'll add this token to the decoder input, and again this loop will be started. Okay, till the EOS token is generated, the loop will be done, and that is what happens in here. Okay, let me show you now. I'm creating the attention mask. It is provided to the model. We are calling the softmax function. We are calling the argmax function to get the token, which is the max one. And I'm just printing it, but this wouldn't be needed. This is just for debugging purpose. And then next we are concatenating that output of a specific step, which is, let's say, the first step along with the start token, the second step along with the start and first token. That happens in here. And we'll do this until the given token is EOS index. And if it is EOS index, then you have generated the tokens completely, and you will stop the loop, and then you are decoding it, which will give you your input. So if you see it in a graphical way, right, it will be like, let's say if I'm saying I am in greedy search, what will happen is it will see like, okay, these are my possibilities: feeling, writing, playing, and it will say like, okay, I'm feeling that the most thing should be something like feeling itself. So I'm going through feeling. Okay, for feeling I'll give it as a red. It will go through this path. Okay, there are some other methods as well known as beam search, which will do something like tree and all. I'll do this as a separate video, like I said. And there is sampling methods, okay, which is top K and top P. All these methods are there, which we'll cover in inference video. Sorry, on a separate video on strategies. So since we have seen how the model will work while we do greedy decoding, now let's see in real time how greedy decoding really works. All right, so let me go to source and let's run python inference.py. As you can see, it's running now, and I have given I am delighted. So anything in the line of 0, which is joy, or I think the only class should be 1, which is joy. Yeah, it is 1. Okay, so yeah, let's try again something. I feel very bad. 0 is sadness and 1 is joy, so here it should be 0. So let's see if that is the case. And yeah, it is 0, and the model seems to be working. We have seen about training, we have seen about inference, we have seen how to create a transformer, we have seen how to create a tokenizer, how to train a tokenizer. Everything is done, but finally we are also going to see how to visualize the attention performed by the model. Okay, so for this I'm using a library known as birdwiz, which will take only the transformer library model. So for now I'm just taking the distill bird model from Hugging Face, and we are tokenizing the input where I'm saying I'm feeling bad that I failed yesterday, and that is provided to the model, and we are taking the attention alone. Okay, let's do a model view where here you can see there are 6 layers in this model and it has 12 heads. Okay, at a given layer and at a given head, how much it is focusing. Let's say I'm seeing the layer number let's say 3 and the 6th head. In the 3rd layer and 6th head, the most importance of CLS is given to SEP, and the I token focuses on CLS, I am, feeling bad, and separator. Okay, am token also focuses on CLS and bad and all. Okay, so here you can hover through this. Okay, and yesterday focuses on SEP. So like this, if you hover it, you can see most tokens always will be either focusing on SEP or will be focusing on CLS. Okay, always it happens. Okay, like as you can see, it is going like that, but also each layer and each head, the layer head at each layer focuses differently, right? Obviously there is a pattern in here, but the lighter ones are slightly different. Okay, if you see here, it is slightly different. So that is what you get with multi-head attention and multi-layers. each layer and each head will focus on different specific entities, and you will have an idea that, okay, I need to focus on this. Let's say I'm going to layer 2 and I'm going to see head alone now. This is not at model level. We are going one level down, 2 layers. At the layer 2, I'm feeling focuses more on SEP, and then it focuses on BAD. If the highlighting is more, it means that the attention is given more to that. Okay, so you can play around this to know how attention works. So yeah guys, that is about this transformers. But yeah, I know you guys are waiting for the announcement. So right now I have planned to ask the questions which I'll post in the community post. Okay, so keep updated to that and keep subscribed to the channel and hit the bell notification so that you'll be either having it in a homepage or else you will get a notification of the community post, and probably you can be the first person to answer it. I'm having 2 ways. I'll also post about this in the community post, but as a viewer of the video, I want you to be the first to know. There are 2 ways I'm planning to do this. Either I'll come live once in a month. We'll discuss about whatever has happened in the month, and at that time I'll put the questions in a probably like Google form, and I'll put the link in the live itself, and you can try to answer in the live and reply me in the comment section, not in the live chat, in the comment section that you have done it or not, because I can't do this in live itself. So post the live, I'll see who has done correctly first, who has not done first, who has done correctly first, and probably we can have them as the winner. That is one choice. But the other one is I'll do it directly in a community post. I'll put the link in the community post and you can try to answer it. But the disadvantage would be people might not get notification and people might miss the chance to answer. So probably I'm leaning towards the first one. I'll be going on a live. I'll put this questions in a Google form link and I'll put it, and probably whoever answers the most correctly at first, and I'll provide the prize to them. So that is what is about the quiz, guys. So let me know your ideas and thoughts on the quiz. I'll see you all in the next video where it is going to be a banger. I'm going to say how I made my best LLM till date in Google Colab itself. Stay tuned for that. I'll see you all in the next video. Until then, cheers.